All right, class, today we're going to be going over the solutions to problem set number 6. Here we're going to be applying our 3 kinematic equations we learned last week to these different situations. So before I do that, I'm going to just write our 3 kinematic equations in the top right of our page here. So first one, we have final velocity is equal to initial velocity plus acceleration times time. Next one, we have final velocity squared is equal to initial velocity squared plus 2 times our acceleration times the quantity final position minus initial position. The last one we have is final position is equal to initial position plus our initial velocity times time plus 1/2 times acceleration times time squared. So again, as we look at our very first problem here, we have a car accelerates on the highway from a speed of 17 meters per second until it reaches a speed of 26 meters per second after 6.1 seconds. We're trying to figure out what is our acceleration of our car. So thinking about our quantities here of initial position, final position, initial velocity, final velocity, acceleration, and time, we want to be able to fill in what we have here. So first thing we know is we're going to be starting out at a velocity of 17.4 meters per second. So initial velocity is going to be 17.4. We're going to accelerate until we reach a speed of 26 meters per second. So that 26 is going to be our final velocity. We're going to be looking at after time of 6.1 seconds. And again, our job here is to figure out what our acceleration is. So in looking at this, again, we can draw just a quick diagram showing what we have here. But we'll say that our car is going to be starting out traveling with a velocity of 17.4 meters per second. Because we're starting out, we're going to be at a t of 0 seconds. Then what we're going to say is that 6.1 seconds later, we are traveling at a velocity that is now a little bit larger at 26 meters per second. So in looking at what we have here, again, we know initial velocity, final velocity, time, and we're looking for acceleration. So based upon these 4 variables, if I scan through our 3 equations we have here at the top, I'm going to say we can't use our second one because we don't have any information about position. We can't use our third one either because we don't have any information about position. So that means I'm going to want to use our very first equation here. So if we're using our first equation of final velocity is equal to initial velocity plus acceleration times time, we can plug in our final velocity is going to be 26. Our initial velocity is going to be 17.4. There we're going to have our acceleration times our time is 6.1. So as we work through the algebra here, first what I'm going to do is subtract 17.4 to both sides. And if we do 26 minus 17.4, that's going to give us 8.6, which is going to be equal to 6.1a. If I divide both sides by 6.1, we're going to get an acceleration that is equal to 1.41. And again, our units are going to be meters per second squared. Again, for these, we're not going to worry too much about significant figures. So as long as you put like 1.4, 1.41, we would give you full credit for that result. Looking ahead to number 2 here, we now have this idea that we have a bullet that's going to be moving through our muzzle, and it's going to leave our muzzle of our rifle at a speed of 600 meters per second. And we know that the barrel is going to be 0.9 meters long. Our job here is we're going to try to figure out what our acceleration is of the bullet while it's moving through the barrel. and we're going to assume that the bullet starts at rest at the beginning of our barrel. So let's say we have the barrel of a gun here, and we know that our bullet is going to start at rest here. So let's say it starts at this side here, our bullet's going to be in here. It's going to have a velocity of 0 meters per second. As our bullet exits the barrel of our rifle, it's going to be traveling with a velocity that we'll say is equal to 600 meters per second. I know that this barrel here is going to be a total of 0.9 meters long. So again, thinking about our quantities that we have here, we're going to have initial position, final position, initial velocity, final velocity, acceleration, and time. So looking at our initial position, we know that our barrel of our gun is going to be 0.9 meters long. So what I'm going to say is that at the beginning here, we're going to be at a position x is equal to 0 meters. So our initial position is going to be 0. Our final position, after we travel to 0.9 throughout the length of our barrel, we'll say this final position is going to be 0.9 meters. In terms of thinking about our initial velocity, again, we say that the bullet starts at rest. So we're going to have initial velocity of 0 meters per second. And we're going to have a final velocity of 600 meters per second. And again, that thing that we're trying to solve for in this problem is going to be our acceleration. So again, we know both our initial and final positions, both our initial and final velocities, and we're trying to figure out our acceleration. So again, if I take a look back up at our 3 equations here, nothing has been given about time. So we're going to say that we're not going to be able to use the first equation. We're also not going to be able to use our third equation, again, because we know nothing about time. But our second equation here has all the variables we need in this problem. It has the initial and final position that we already know. It has our initial and final velocities that we already know. And it has our acceleration that we are going to want to be solving for here. So we're going to want to pick equation number 2. So we scroll back down. That equation we want to use is velocity squared is equal to initial velocity squared plus 2 times acceleration times final position minus initial position. So plugging our values, we're going to have 600 squared is equal to 0 squared plus 2 times acceleration times a quantity 0.9 minus initial position of 0. So doing a little bit of math here, 600 squared is going to give us 360,000, or 360,000. 0 squared is going to be just 0. We're going to have plus 2 times a times 0.9. So 2 times 0.9, that is going to give us 1.8. So we're going to have 360,000 is equal to 1.8 times acceleration. I'm going to divide both sides by 1.8 here to isolate our variable a. And this is going to be give us an acceleration that is equal to 360,000 divided by 1.8, which is going to give us 200,000. And it should be in terms of meters per second squared. So yeah, when we think about how quickly this bullet's going to be accelerating, it's going to be at a huge, enormous rate of of 200,000 meters per second squared. Moving down into question 3 here, we have Susie Oftowski has reached the end of a ski slope and abruptly decelerates from 29 meters per second down to 1.8 meters per second in 1.45 seconds. So, our initial velocity is going to be 29. We're going to be dropping down to a velocity of 1.8 meters per second. It's going to take us 1.4 seconds to do so, and we want to figure out what our acceleration is. So here we have our person traveling on skis. They begin by moving at a rate of 29 meters per second. We'll say this is at our time of 0 seconds. 1.45 seconds later, this person is going to be traveling at a much slower rate here at a velocity that is only 1.8 meters per second. This happens 1.45 seconds later. So you're thinking about our variables here. We have initial position, final position, initial velocity, final velocity, acceleration, time. We know that our initial velocity is 29 meters per second. We know that our final velocity is 1.8 meters per second. In this problem, we're trying to figure out what our acceleration is. And we know it takes us 1.45 seconds to do this. So again, looking at our kinematic equations here, we know initial velocity, final velocity, time, and our acceleration is what's missing. So right now, nothing's been stated about our initial position or final position. So again, when we scroll back up to our 3 equations here, we don't know anything about position, so we can't use 2 or 3. So we're going to want to use equation number 1 here that has those variables we need. So if we go, final velocity is equal to initial velocity plus acceleration times time. We're going to have 1.8 meters per second is equal to 29 meters per second plus our acceleration times our time of 1.45. First thing I'm going to do is subtract 29 to both sides. So we do 1.8 minus 29. That's going to give us a negative 27.2. It's going to be equal to 1.45 times A. Divide both sides by 1.45. It's going to give us an acceleration that is equal to negative 18.8 meters per second squared. Yeah, we want to do a quick double check to make sure our answer seems right. We have a negative acceleration, which should make sense to us because we are slowing down as we go from 29 down to 1.8. Now, what part B of our question is asking is, what distance have we traveled? So what we're going to say is, again, same exact situation here. So we're going to recopy down our chart here of the different values we know. So from the problem that was given to us, we knew that our initial velocity was 29 meters per second. Final velocity is 1.8 meters per second. Time was 1.45 seconds. And now we know that our acceleration is negative 18.8 meters per second squared. So our job is to figure out what distance Susie traveled. Now, one kind of final assumption we can make is we want to know the distance we've traveled. So the easiest way to find distance is we'll just say we start off at a position of 0 meters, and then whatever our final position would then be equal to the distance we've traveled. So again, as I take a look at this information we have here, everything except our final position. So if I scroll back up to the top here, I want to choose one of my kinematic equations. We could use either our second one or a third one actually. We have a piece of information about all of those. I'm going to go ahead and just use our third equation here because it's already just final position is equal to something, so we're going to have to do just a little bit less reworking with our algebra. But again, either our second equation or our third one, they both would give us the right answer. I'm going to just do this problem with our third equation now. So if we scroll back down here, using that third equation, x is equal to x initial plus v sub 0t plus 1/2 times a times t squared. Final position is what we're looking for. We keep it as x. X initial is going to be 0. Our initial velocity is going to be 29 meters per second times our time of 1.45. We're going to add that to 1/2 times our acceleration, which in this case we have negative 18.8. Again, extremely crucial we keep that negative sign in there. And then our time squared is going to be 1.45 squared. So to simplify this a bit, again, we're going to have our 0. I'll just cancel that out here. We do 29 times 1.45. That's going to give us 42.05. If we do 1/2 times negative 18.8, that is going to give us a negative 9.4. And then 1.45 squared is going to be equal to, well, roughly 2.1. So again, next thing we're going to want to do is that last multiplication here. And we are going to get a result of x is equal to 42.05. Going to add that to a negative 19.72. Again, here, when I plug these values into the calculator, I use the unrounded ones. So instead of it being 9.4, is really negative 9.379. So what I plugged in my calculator was a full number, but just in writing it down, I simplified a little bit where I rounded, but this would be our kind of unrounded answer down here for our negative 19.72. So next up, we want to add 42.05 to our negative 19.72. This is going to give me a final x value or distance we've traveled of 22.3 meters. Final question we have here to conclude problem set number 6 is we have an airplane reaches cruising altitude while traveling at a speed of 134 meters per second. From there, the airplane is going to accelerate at a rate of 0.2 meters per second squared. We want to know how far our airplane's traveled after 24 seconds. So what this is going to look like is we have our airplane. It's traveling at a speed of 134 meters per second. It's going to be accelerating at a rate of 0.2 meters per second squared. And we want to know that after 24 seconds, we want to figure out how far we've traveled. So yeah, creating my table over on the left here, we have initial position, initial velocity, final velocity, acceleration, and time. So when we think about our initial position, again, we're just trying to find how far our distance we've traveled. So we'll say we're going to begin at an initial position of 0 meters. That way, whatever our final position will tell us how far we've traveled. Our initial velocity is going to be 134 meters per second. At this point, we actually don't know any information about our final velocity, so we'll leave that blank for now. But we do know our acceleration is going to be a positive 0.2 meters per second squared. And we're trying to figure out what happens after a time of 24 seconds. So taking a look here, what we're trying to solve for is our final position, how far we've traveled. And we know initial position, initial velocity, acceleration, and time. So scrolling back up here, if you look at our first kinematic equation, we can't use that because that doesn't allow us to solve for final position. If I take a look at my second kinematic equation, I actually can't use that one either because I don't know anything about our final velocity. But our third equation we can use. What that third equation is going to allow us to do is figure out what our final position is. So, scrolling back down, we're going to have final position is equal to initial position plus initial velocity times time plus 1/2 times acceleration times time squared. So final position is unknown, initial position is 0, our initial velocity is 134, our time is 24 seconds, do times 1/2 times 0.2 times our 24 seconds squared. So we do 134 times 24. This is going to give us 3,216. That's going to be added to, we'll first do 0.5 times 0.2. It's going to be 0.1 times, and we'll take 24 squared. It's going to be 576. So my next step, if I take 0.1 times 576, that's going to give me 57.6. So x is equal to 3,216 plus 57.6. My final position, telling us the distance we've traveled, is going to be the sum of those two values, which is equal to 3,273.6 meters.